Hello everyone, welcome to this tutorial. In this tutorial we will continue with the reaction series. Here we will talk about how to model the heterogeneous catalytic processes using Aspen Hysys. So this is a continuation of the reaction models. So this particular model is quite similar to the kinetic model. So I would urge you to actually check out the kinetic modeling tutorial before you start up with this. But if you have done that, you can actually stay with me, right? So now we have the heterogeneous catalytic model. Now this model is otherwise known as the Langmuir-Hinshelwood-Hugin-Watson model. That is the LHHW. So if you see it like that in other cases, you know that we are referring to the heterogeneous catalytic model. So you will actually see it as LHHW in the Aspen Plus, for example, the Aspen Plus software, and you may see it like that in maybe books or journals, right? So we're actually referring to the same thing, right? And basically it deals with processes that involves the use of catalysts, right? The use of catalysts, and these catalysts are usually not in the same phase with the reactants involved in the processes, right? So that's where this particular model comes in. It comes in where you have cases where you use catalysts for those processes and those catalysts are not in the same phase with the reactants, right? The basic expression for the rate law for the heterogeneous catalytic process is actually this one we have on the screen, which is R LHHW is equal to the kinetic factor multiplied by the driving force all over the adsorption, right? So this particular expression is quite similar to the kinetic expression. The major difference is actually the adsorption, right? The adsorption, the denominator, right? So you have kinetic factor multiplied by driving force all over adsorption. So this adsorption term is actually the major difference between this heterogeneous catalytic model and then the kinetic model, right? So if you have an understanding, a proper understanding of the kinetic model, then this heterogeneous catalytic model will not be so much of an issue, right? So much of an issue to you. So let's get ahead with it. So now if we are using a base reaction, right, just for illustration, we have W plus X to give you Y plus Z, right? And we have that the rate expression is equal to the kinetic factor multiplied by the driving force all over adsorption, right? Now if you are to further break that down, you have what we have in the equation below. You have rate is equal to K multiplied by E raised to power minus E over RT into KF, which is the kinetic factor of the forward reaction multiplied by the concentration, the concentration of the reactants minus KB, right, which is the kinetic factor of the backward reaction multiplied by the concentration of the products all over the adsorption expression, right? So basically this is the rate expression for the reaction above, which is W plus X to give you Y plus Z, right? And from the equation you can see that it's a reversible process. It's a reversible process, and that is why in the rate expression you have the backward kinetic expression as well, right? So going down, so going down, we have the rate expression for irreversible processes, right? For irreversible processes, you majorly have that Kb is equal to 0, right? So there is no backward reaction. There's no backward reaction. So you would only have a rate expression for the forward reaction all over your adsorption expression or your adsorption term, right? So then you have also for the forward reaction as well, right? Okay, before we go into the forward reaction, you also have the adsorption term or the adsorption expression, which is which takes this format, right? This format we have here, right? So this is what an adsorption term actually looks like, right? So basically these rate expressions are usually gotten from experimentation. So you can actually get them from probably books or research papers as well, right? So this is an example of a heterogeneous catalytic model. Let me see. I'm looking for the okay. Scroll up. Okay, so the first this is for irreversible. So the first one we looked at was for reversible processes. So I skipped that. So this first expression we talked about here is for the reversible, right? So you have the forward kinetic expression and the backward kinetic expression all over the adsorption term, right? So this is actually for a reversible process, right? So yes, and I said it earlier that you can see that the process is actually reversible. So we have for the reversible, and then for the irreversible process, Kb is equal to 0, and you don't have a backward reaction, right? So, and then you have this as an example of how an adsorption term should look like, right? This right here. So now, taking that into consideration, we can look at these heterogeneous expressions that we have. So for this first one, we have this reversible process, right? So you know it's reversible based on the arrow. So the arrow is facing the backward side and the forward side as well, right? So you know that this is actually a reversible process. Now from here, see the forward expression, the forward kinetic expression, we have the backward kinetic expression, then we have the denominator term, right? This is the denominator term. You have the division sign, and then you have the denominator term, right? So from here, from this expression, we can deduce that this rate expression is based on catalyst weight, right? This particular rate expression is based on catalyst weight, and this is because we have the unit for rate here as kg cat, right? So you can see it from the expression. You see kg cat dot second. So you know that this is actually a rate expression based on the weight of the catalyst, and this will be best modeled using Aspen Plus, right? Because of this, because Aspen Hysys works only based on reactor volume, right? So you can see that. Then you can also see other data from this. So so because this is a reversible process, you have Kf and you have Kb, right? So you have the kinetic factor for the forward and the backward reactions respectively. Then you have the concentration basis is partial pressure, right? From our kinetic lecture, you would have noticed that we talked about concentration basis, right? And the concentration basis for this particular rate expression is P, right? So we know that it is partial pressure, right? And then you have the denominator term here, right? This is the denominator term. Then you have the denominator exponent to be 1, right? So these are some of the deductions you can actually make from this particular rate expression, right? So going forward, we have this one as well, right? So for this one, this is a forward reaction, so it doesn't have a backward. This is not a reversible process, it's just a forward reaction. So you have reactants to form products, right? So there is no backward reaction in this particular case, right? So it's just the reactants coming together to actually produce these products, right? So you only have the forward expression on the numerator, you only have the forward expression, and then you have your denominator term, right? And for this one, the rate is based on reactor volume, right? As you can see, the rate is based on reactor volume because we have meter cube in the rate units. You have meter cube, so you know that this is based on reactor volume, and this can be modeled using Aspen Hysys, right? Then you also have the concentration basis here is based on this should be molarity, right? Molarity, because this is C, right? This is C, so you see that this is molarity, right? So you have your numerator, which is your kinetic factor, and then you have your adsorption, which is your denominator, right? So you can see different deductions from this particular expression, right? So basically that's how these rate expressions work. So it is very important that you understand how to actually interpret these rate expressions because they will affect the as your output is based on the kinetics you actually input, right? And also you can see here that the KB is equal to 0 because it's just a forward reaction, right? So based on this knowledge, we would actually we'll be solving a problem. So we'll make this tutorial problem based. So we have this right here. So we are going to be modeling the production of styrene, right, from ethyl benzene, and the details of this particular model is here. So you have your equation, and then you have your kinetic data, right? So we are going to be making use of all of this, right? All of this. So we have the equation here, which is a reversible process, right? This is actually a reversible process. So you have ethyl benzene reacts to give styrene and then hydrogen, right? And then this is the rate expression. This is the rate expression. So you have R1 is equal to K1 into PEB minus 1 over KE PST PH2 all over 1 plus KST PST, right? So here you can see that they gave both the forward expression and the backward expression, and this is because it's a reversible process, right? So you have more data down here. So you have K1 is equal to A1 e raised to power minus E1 over RT, which is the normal Arrhenius equation, right? Arrhenius expression. Then you have K inverse, which is KB, which is the kinetic factor of the backward reaction, is equal to KF or K1. So K1 is the KF, which is the kinetic of the forward. So you have K1 over KE, which is the equilibrium K. So K inverse, as I said in the kinetic tutorial, K inverse is equal to K forward over KE. So you have this A1 over AE e raised to power minus E1 minus EE over RT, right? So you have to resolve all of this in order to get the K inverse values, right? And then you have the values for those different parameters. You have ln AE is equal to 27.16. So if you do if you take exponential of both sides, you will get the value of AE, right? And then EE is given, A1 is given, E1 is given as well, right? And then you have KST, right? So KST is the adsorption term, the adsorption term of styrene, right? So you have 1 plus KST PST, right? So the KST is the adsorption term of styrene, right? So based on that, we can actually resolve this rate expression and input the values where necessary, right? So, and this particular rate expression is based on partial pressure, right? Because we have the concentration basis is P, as you can see, right? It's P, PEB, PST, pH2, right? So we know that the concentration basis is partial pressure, and then the rate expression is based on reactor volume, right? Because see, the A1 is equal to 3,524.4 kilomole meter cube, right? Kilomole per meter cube per second, right? Kilomole per meter cube. So we know that this is based on reactor volume. So we can actually model this using Aspen Hysys. So based on what we have, we can actually derive this expression. So by the time you do all your calculations and you plug in the values, this rate expression above, this particular one, this one here, if you can see my cursor, this one here turns into this, right? So this turns into this right here, right? So this is what we'll be using to actually model the process. This is what we'll be using to model the process. So quickly we can go into the simulation environment. So let's add the reactants and products. We have ethyl benzene. Yeah, ethyl benzene. Yes. To give you styrene. Yeah, styrene. And hydrogen, right? H2. Yes. So these are the components we are working with. For fluid package, let's just make use of pengrobinsin for this illustration. So we'll use pengrobinsin, then we can go into the simulation environment, right? So yeah, we are making use of the plug flow reactor. So we go into the reactor section of the palette. You can see my cursor, bottom left, right? So we have this is our plug flow. So we can create material streams in it. Then we can start the specification, right? Okay, RPD. Okay, yeah. So it says requires a reaction set. So let's quickly get our reaction specification done before we continue with the modeling. So for that, you go to reactions, right? And you click add, right? That's the first step. You must have noticed from previous videos. Then you click add reaction, and like I always tell you, ensure your reactant source tallies. So when you are sure that it tallies with your component list, you now choose the model you want. In this case, the model is the heterogeneous catalytic, right? So you click that and then you click add reaction. So once you do that, you can actually begin your specification. So we have ethyl benzene to give you styrene and then hydrogen, right? So you can easily balance this. Yes. So once you do your balancing, let me see. Okay. So once your balancing is correct, your balance error should be 0, right? And then you can do other specifications. I think the basis is partial pressure. Yes, basis is partial pressure. Base component is ethyl benzene, right? This should be PA Pascal. Yes, we can also confirm that. So let's check from the yeah. So from here you can see it's Pascal. So it's Pascal we are using, and also from the A value of the equilibrium is also Pascal. So it's Pascal, then it's kg mole per meter cube, kg mole per meter cube per second, right? So kg mole per meter cube per second, and then Pascal, right? So this is good to go, right? Then you have your reaction rate. So in your reaction rate section, you have the numerator, you have the denominator, right? Under the numerator, you have the forward and you have the reverse. For reversible processes, you specify both the forward and the reverse. For irreversible processes, you specify only the forward reactions, right? So basically that's it. So so we have the values, so it's just to input them. So you see the values here in this particular expression. So this is what we are using to actually specify those sections, right? So this is for the numerator, these are the numerator values, and then these are the denominator values, right? So for the numerator, you are specifying your values for A and E for both the forward and the backward reaction. So this you have 3, yes, E3. So this is the value for A, and then E is 1.586 E5, right? Yes, that should be the value, 1.586 E5. Yes, because A1 is 158.6, right? So that's for that. Then for the next one, we have 5.6. That's for reverse. 5.6448 e raised to power minus 9, right? This is the value, 5.6448 e raised to power minus 9. Then we have 34340, right? So if you still have issues trying to understand these kinetic parameters, I will urge you to watch the kinetic video, right? So basically you are just inputting the pre-exponential factor value and then the activation energy value into the numerator, right? That's basically what you are doing here. That's exactly what you are doing here. Then you now specify your forward order and reverse order values, right? So this is based on the concentration basis exponent, right? So the values you specify in the forward and reverse order is based on the concentration basis exponent. So so for that you can still check the rate expression. So for the forward, you have PEB, right? PEB is also PEB raised to power 1, right? So it means ethyl benzene forward order exponent is 1, right? Because you just have PEB, right? And then for the backward, you have PST pH2, right? The P stands for pressure, right? So the concentration basis is pressure, and the exponent is 1, right? Because it's PST. PST is the same as PST raised to power 1. pH2 is the same as pH2 raised to power 1, right? So that is what you are inputting in this section, right? So these are the default values, but based on what you have in your rate expression, you are supposed to edit them, right? Based on what you have in your rate expression. But in this case, they are already correct, so I would leave them without editing them, right? So you have PST, pH2 for reverse, and then you have PEB for forward, right? So all of them are 1, right? 1, 1. So they are correct, right? So we can leave this section and go to the denominator section. So for the denominator section, we have the adsorption expression, which is 1 plus 1.3 times 10 raised to the power minus 4 PST, right? So we'll be specifying this in the denominator section. So basically, in this denominator section, you can actually ignore the 1, right? Because most denominator expressions always start with 1, right? So, but when you are specifying it in Aspen Hysys specifically, you can ignore this value and start specifying from the next expression, which is this value, right? So you can actually ignore this 1, right? So, but it is not to be ignored in Aspen Plus though, right? So here you specify the A value, you specify the activation energy, then you specify the exponents, right? The component exponents, right? So yeah, so in this case, the expression we have, this right here does not have an activation energy value. So this value 1.3 times 10 raised to the power minus 4 is equivalent to A, right? It is actually equivalent to A, so we'll be inputting it there in the A section of that first table. So that will be 1.3. So that's 1.3 e raised to the power minus 4, right? So e raised to the power minus 4. Now then the activation energy is 0, right? Activation energy is 0. Then the exponent is for only styrene, right? It's for just styrene. Let's check it. So you have PST. So as you can see, PST. So you are specifying an exponent value for styrene in the denominator, right? Because you have 1 plus KST PST, right? So we have KST value here, and then we have plugged it into the reaction expression, and then we have PST. So PST is 1 because PST is still the same as PST raised to power 1, right? So this is 1. Specify 1 here. Sorry about that. Specify 1 here, and you are good to go, right? So hydrogen and benzene are 0 in this case, right? So with these specifications, we can actually continue with our modeling. Yeah, we can continue with our modeling, right? So our specifications are correct, right? So if you have more terms in your denominator, you keep specifying them in different rows, right? So if you had another term, for example, you specify it in this next row, right? So each row is for a particular term on your denominator, right? So once you are done specifying this, you can exit this window and then add to FP, add to FP. So right, add to FP, and we are ready to model the process now, right? So everything is fully specified in this particular scenario or tutorial, right? So we can go and continue with the modeling. So with that, we go back to the simulation environment and we can run quickly. So for we have our specifications. We have initial temperature and pressure for the feed. We have that here, so we can quickly specify that. We have 630. We have 630 degrees Celsius, then 137.8 kPa, 137.8 kPa. Then I think we specified the molar flow. We should specify molar flow for this one. Yeah, mole flows, yes. Okay, so let's check the mole flow. So the mole flow is ethyl benzene and steam. Okay, so we need to add water to this process. Let's just add water. We need water in this process. Close this. So I will just add water to the process quickly. Yeah, H2O. Yes, so we can specify that. Do you wish to be left in holding mode? No, I don't want to be left in holding mode, right? So holding mode is about your solver. Your solver has to be active so that your simulation can solve. I've said that in our introductory tutorials. So let me see. So we have 150 kg mole per hour of ethyl benzene and 15 kg mole per hour of steam, right? So we can go back and specify mole flows. So I'm clicking basis as mole flow. So I'm entering the values directly without specifying the mole fraction, right? So let's see how that works. Ethyl benzene is 150, right? Yeah. So total is 165 kg mole per hour. You click OK, right? And your stream is fully specified. Then Hysys can calculate, it can calculate the molar composition or the mole fraction. Yeah. So this is the mole fraction of the feed based on the mole flows specified. So we can exit this, I think. Yes. So that's for that. Then we can specify the PFR right now. So for the PFR, it says requires a reaction set. So we are going to attach the set we just created, set 1. So we have specified that, and it says unknown dimensions, right? Unknown dimensions. So with the dimensions, we have reactor consists of 500 tubes. It's a multi-tubular reactor, yes. So reactor consists of 500 tubes. So you have number of tubes 500. That's the first specification, number of tubes 500. Then we have internal diameter of 6 cm. Diameter 6 cm. So you can actually tweak your units here with the drop down. Then you have, what else do you have? You have wall thickness of 5 millimeter, wall thickness 5 millimeter, and length of 4 meter, right? So wall thickness is 5 mm. I think this is correct, right? So if you use mm, it will convert it back to meter. Yeah, so that's correct. So 5 mm, then length of 4 meter, right? Yes, length of 4 meter. So that's correct too. Length of 4 meter. Then it says the tubes are filled with catalyst particles of spherical geometry. The particles possess a diameter of 5 millimeter. So we have to specify particle diameter. Yeah. To actually specify particle diameter, you have to activate catalyst data. This catalyst data section under reactions, you have to activate it, right? But the only way to activate it is to specify a void fraction or a bed voidage, right? Bed voidage. So the bed voidage specification is based on reactor volume. So yeah, that is as regards Aspen Hysys, is based on reactor volume. So it says the tube voidage fraction, or the tube void fraction, is 0.45. So by the time you specify that, it activates the catalyst section. Now you see, when the void fraction is 1, right? When the void fraction is 1, you see that the catalyst data is not activated. But once you change it to a fraction, right, that is probably less than 1, it activates that section, right? So it activates it. So you can now make some specifications here, specifications such as the particle diameter, which is what we are supposed to input, then the particle sphericity, then the density, the solid heat capacity. You can specify such values for your catalyst when you have activated the catalyst section. So we have particle diameter of 5 mm, right? So 5, this should be 5, sorry, yeah, 5 millimeter. So use the drop down and you specify millimeter. So basically this is it, right? So we are done with our specifications. It has already calculated the total volume, right? The total volume, right? So yeah, so basically with this we can actually solve this particular problem. Now it says unknown delta P, right? Unknown delta P. So delta P has to do with either you specifying it yourself or allowing the software to calculate it using the ergon equation, right? But in this case, I would use the ergon equation to actually solve this particular problem. So I will just click on it. So if you want it to calculate it by itself, you click on ergon equation. But if you want to specify your delta P yourself, you can actually specify it by typing a value here, right? So I just click on this and it actually solves the model, right? So we can now see our products. Yeah, we can see our products. Okay. Okay, so from here, there has been no reaction yet. There has been no production of styrene. So I will check. Let me look at my, yes, and from what I'm seeing, we also have hydrogen produced, right? Hydrogen is also produced. So I want to change this reaction phase. I want to use overall instead of using aqueous, right? Because hydrogen is also involved in the process. So I'll use this overall as my reaction phase. Then I forgot to talk about the denominator exponent, right? The denominator exponent for this particular rate expression is 1, right? Because you can see that from the expression. So let's see. So this in brackets is like 1 plus kst pst raised to power 1, right? So I'm going back to the model now. So I change this to overall to see if it will actually lead to a reaction. Yes. Okay, so let's check if there was production. Yeah, as you can see, the molar flow has changed. So I believe that, yes. So you can see that there has been production of styrene, right? So there's production of styrene right now. So based on that, we can check the reactions. So to check the conversion of the reactor, you click on reactions and you check results, right? So this is the conversion. The conversion is 23.84, right? 23.84%, right? Based on the specifications we have made, right? So that is the conversion, and then this is the composition, right? This is the composition of the reactor product, because I believe that was what was asked for in the question. Let me see. Yes, it says what does it say? Determine the conversion of ethyl benzene and the composition of the reactor output, right? So based on both of those, we have the composition of the reactant, the product, the reactor output, right? This is the composition of the reactor output, and then this is the conversion of ethyl benzene, right? So yeah, you can see base component ethyl benzene, and then this is the conversion 23.84, right? Based on the specifications we have made, right? So you can actually optimize the process. You can play around with the dimensions of the reactor. The case studies can actually help you optimize the different parameters as regards the reactor dimensions and then the process conditions, right? The process conditions of this particular process, right? So you can actually do case studies on this particular model, right? If you don't know how to do case studies, you can check the case study tutorial, right? If you need links to the tutorial, you can let me know in the comment section, right? Either for the kinetic or the case study tutorial, right? So still checking the composition, you can actually check it from the stream as well, right? So this is the composition of the reactor product, right? So basically we have been able to solve this problem, and I have been able to illustrate how the heterogeneous catalytic model is actually utilized in the Aspen Hysys software, right? And with that, we have come to the end of this particular tutorial. If you have questions on this particular model, kindly let me know in the comment section. Then if you need links to any of the previous reaction videos, the video on kinetics, the video on sensitivity analysis or case studies, you can actually let me know in the comment section. Then if you have any general questions, you can also share them in the comment section. Like this video, share with your friends, subscribe to this channel if you have not done so yet to actually get notification on subsequent tutorials. Thank you for joining me in this particular tutorial. Do have a good day.